Okay, we've been discussing for the last few weeks now the deep freeze of the Siberian woolly mammoths. And we closed last week with an explanation of this deep freeze, which was the collapse of the antediluvian thermoblanket as the water vapor condensed out as precipitation in the form of rain. Then this condensing out as precipitation caused the collapse of the thermoblanket, which was one of the things, the major thing, that resulted in the catastrophic deep freeze of the Siberian woolly mammoths. Now, please, while you're sitting out there, don't be forming questions in your mind while I'm up here teaching you, because you're forming questions at the same time I'm giving you the answers to your question. Some of you wanted to know why did it get cold up at the poles? And I spent the whole week last week telling you why it got cold at the poles. And then some of you wanted to know, well, what else have they found up there? As if an estimated 5 million woolly mammoths is not enough. So anytime you get into an area that's new to you, it doesn't matter whether you're in school and you're talking about geophysics or you're just talking about some simple subject, if it's something new to you, you'll always miss all of it or a lot of it the first time. That's just part of learning. You always miss it. Now, you think that you heard everything that was said until you go back and hear the tape. And it's true in so many areas, you'll find out that your question was already answered somewhere on that tape, because I went back and listened to it, and all of those questions that were asked last time were answered during the message. It's rare when you get a question that I meant to deal with and I didn't deal with it. Somewhere, something has been said that if you'll just think about it later on, it won't register all on your mind right away. But if you'll think about it later on, you'll find out that the answer's already been provided. So don't spin your wheels out there. You've got enough to do to stay up just taking notes. And if you try to stay up, plus try to stay ahead of what I'm saying by thinking, all right, now, that couldn't be because of this, and I'm telling you why it could be while you're thinking that. But you see, you're missing that because you're thinking in your mind, oh, it couldn't be because of this that I'm thinking of. And then we're giving you the answer. So it's cold at the poles because of the tilt, 23.5 degrees of the Earth on its axis. That's very simple. That's something that we shouldn't have to prove. That's just something that everyone should already know. Obviously, if you've got a tilted surface with some type of heat source aimed at that surface, if it's tilted, it's not going to receive the full benefit of since it's the sun, the solar energy. That's why, although the United States is closer to the sun during the wintertime, it's colder because it's tilted during the wintertime, and it's not tilted whenever it gets back around in its trajectory path around the sun. During the summertime, it's further away, it's not tilted, and so the sun can have full impact. But at the poles, that's where it's tilted the most. That's where it's going to be the coldest, because although it's still getting sunlight and solar energy, much of it's reflected off. Now, I want to sum up and wrap up what we've been saying about the mammoths with an eyewitness account from a Russian surveyor that will tell you just what we've been telling you the last few weeks. Now, it's impossible to get all this down. It's a couple of pages here, but you might want to listen because it's very interesting. Now, this is a quote from a surveyor in Russia of what they discovered. This is picking up in the middle of the story. They're out surveying in a boat, though. This is during the summertime. And he says, our patience had been tried, but suddenly a huge, black, horrible mass bobbed out of the water. We beheld a colossal elephant's head, armed with mighty tusks, its long trunk waving uncannily in the water as though seeking something it had lost. Breathless with astonishment, I beheld the monster hardly 12 feet away, with the white of his half-open eyes showing. The position of the beast interested me. It was standing in the earth, thus indicating the manner of its destruction, not laying on its side or back as a dead animal naturally would. Now remember, we pointed that out before. All dead animals end up on their side. The soft peat or bog on which it stepped thousands of years ago gave way under the weight of the giant, and he sank as he stood, all 4 feet, unable to save himself. A severe frost came, turning into ice both him and the bog, which overwhelmed him. That's what we had said, that as the water vapor began to condense out as rain, as precipitation, and fell, then that's where you end up with the muck in the region. It turned everything to a watery mass. And as this particular specimen was walking along, he sunk in a bog of peat and of mud, sand, and so forth. And it wasn't until after he sunk that the temperatures began to fall. You see, you had to have the collapse first to let the heat out, and after it had begun to collapse, you wouldn't wait the full 40 days. After it had begun to collapse, then you'd have the temperatures plunging down to several hundred degrees below 0 Fahrenheit. He calls it a severe frost because he doesn't understand what happened. But a severe frost is not going to catch a mammoth. We've already shown you that before. But he says a severe frost came, turning into ice both him and the bog, which overwhelmed him. He goes on to say, picture to yourself an elephant with a body covered with thick fur, about 13 feet in height and 15 feet in length, with tusks 8 feet long, thick and curving outward at their ends, weighing several hundred pounds each. A stout trunk 6 feet long, colossal legs 1.5 feet thick, and a tail bare to the tip. The beast was fat and well grown. Death had overwhelmed him in the fullness of his powers. His large, parchment-like naked ears lay turned up over the head. The whole appearance of the great beast was fearfully strange and wild. Then he goes on to give a comparison or a contrast between it and the Indian elephant. And then next paragraph, he says, I could not divest myself of a feeling of fear as I approached the head. The open eyes gave the beast a lifelike aspect, as though at any moment it might stir, struggle to its feet, and bear down upon us with a stentorian roar. A bad smell in the carcass warned us that it was time to save of it what we could, and the encroaching river, too, bade us hasten. First, we hacked off the tusks and sent them aboard our boat. Then the natives tried to hew off the head, but notwithstanding their efforts, this was slow work. They never did make it. As the belly of the brute was cut open, out rolled the intestines, and the stench was so dreadful that I could not avert my nausea and had to turn away. But I had the stomach cut out and dragged aside, and it was well filled. The contents were instructive and well preserved. The chief contents were young shoots of fir and pine trees. A quantity of young fir cones also, in a chewed state, were mixed with the mass. And then the one who's telling the story ends his statement. The one who's commenting on it goes on to say that unfortunately they never got the animal because the river was coming up on them fast where the animal was stuck and carried him away. They did end up with another one that they took back to the museum in Leningrad. And of course we've got the famous one, Beresovka, that was discovered back in the early 1900s, early part of this century, that was taken there in perfectly well-preserved condition. And as far as I know, I've never been to the museum, Russian Academy of Sciences in Leningrad. If you're ever there, you can check and see if Beresovka is still there. But assuming that he isn't, it doesn't really make any difference because of all the specimens that have been found in this area. Now, what this conclusively tells us is that the collapse of the canopy is what caused the tremendous cold that immediately resulted in this region. The next question we have to raise then is, if the collapse of the canopy of the thermal blanket, the antediluvian thermal blankets, is what caused it to become cold, then what caused the canopy to collapse? What caused it to collapse? There is a particular natural process, although it was triggered supernaturally, that caused the antediluvian thermal blanket to collapse. If you'll turn back to Genesis chapter 7, we'll look at an important verse that we looked at before, or the most important verse, verse 11, as far as the origin of the flood waters is concerned. Now, if you'll think back, we did a whole message on various theories of the origin of the flood waters. We went over a whole host of theories that people had dreamed up in trying to come up with the answer of where all this water came from. As I've said before, if all of the water in our atmosphere and all the clouds condensed out as precipitation, we'd have about 2 inches of water all over the earth. Now, if we could get all the seas out of their banks and we could level the land, raise all the valleys and level the hills, we'll end up with 12,000 feet of water on the earth. Now, we don't need 12,000, but 2 inches is not enough. We need something in between that. And one of the theories, one of the erroneous theories that we had covered under that message was the volcanic theory, that a whole host of hundreds and hundreds of volcanoes all happen to go off at the same time. And since volcanoes spew out an immense amount of steam as well as water, then this, they say, hypothetically, they're theorizing, would have been enough water in order to cover all of the Earth's surface. And we said that that theory falls down under the fact that when you've got that many volcanoes all erupting at the same time, you put too many poisonous gases in the Earth's atmosphere, and it would have killed not only all of the beasts, but it would have killed the ones on board the ark, which were not supposed to be killed. But if you'll also remember, I didn't say that there weren't any volcanoes. I just said there weren't thousands and thousands of them erupting because the gases would have killed everyone. No, I didn't say that there weren't any, because as a matter of fact, there were quite a few volcanoes that went off, and they are the immediate trigger that caused all of the water to, or the vapor, to condense out as rain and to precipitate upon the earth. Now, if you'll look in chapter 7, here in verse 11, this is what we see. I didn't say that there weren't any volcanoes. I just said there weren't thousands of them. There were plenty of them. We don't know how many. There are 500 active volcanoes today and 1,500 extinct volcanoes. Now, that doesn't have to mean that all 1,500 of those, the ones that are extinct, are the ones that went off in 7:11, Genesis 7:11, because we've still got several thousand years after the flood before us when volcanoes have been going off all the time. And that could have been the period when one of these 1,500 extinct ones went off. But since there are only 1,500 extinct volcanoes, we can't have thousands and thousands that went off because there's only 1,500 that are extinct. And what's interesting, you think, well, the floods would have destroyed the volcano. No, because Mount Ararat, upon which the ark landed, is one of the 1,500 extinct volcanoes. That's told us over in chapter 8 that Ararat was the mountain chain upon which the ark finally landed, and Ararat is an extinct volcano. Now, whether it was one of the ones going off that caused the collapse of the canopy, we don't know. If it didn't, then it would have been one of the ones that would have come subsequent to that, but prior to our time. The 600th year of Noah's life, in the second month, the 17th day of the month, the same day, were all the fountains of the great deep broken up, and the windows of heaven were open. Now notice the order in which the sacred historian is providing us with the source of the flood waters. The windows of heaven don't open prior to the breaking up of all the fountains of the great deep. The fountains of the great deep break up first in our verse because they broke up first chronologically in history. Now, when it talks about the fountains of the great deep, it's referring to subterranean water, because that word deep, as we saw in that message over in Genesis 1, does refer to great depths of water, but much of it had been locked up under the surface of the earth under tremendous pressure. Now, it didn't all come forth in volcanoes. In some places, there were simply splits in the ground, in the land, out of which sometimes came lava, many times just came water. Nonetheless, one of the things included here in chapter 7 and verse 11 happens to be volcanoes, because we know they had to have erupted at some time. And as we'll see here in the message, this is the one thing that helps prove to us naturally what could have caused the collapse of the antediluvian thermal blanket. Now that's what we have to go back to, the water vapor canopy. We have to go back to this and understand a little bit about it in its relationship to the Earth's atmosphere. Now I have a diagram here to show you something about the Earth's atmosphere and the levels of the Earth's atmosphere that you might want to get down. Now, it all depends how many layers you end up with. It all depends on your own division, because there are many more divisions than what I've got. I've got the basic ones: troposphere, stratosphere, mesosphere, thermosphere. There are other regions like homosphere, biosphere, and several other, but a lot of these you'd bracket out here because they would include like 2 or 3 of these and so forth. But these are the 4 that are generally discussed when you're discussing the levels of the Earth's atmosphere. Now at the bottom, you've got Earth. Above that, the troposphere. Now the figure in miles is an average figure because it fluctuates depending on the time of year, as well as your position on the Earth. Whether you're at the pole, it's going to be lower; at the equator, it's going to be higher. But this is the region, say the troposphere, for example. This is the region in which we find it. It extends 11 miles up above the Earth's surface. I think generally you'll see anywhere from 7 to 11 miles. 7 miles at the poles, where your atmosphere is closer together, your layers and levels are closer together, and higher at the equator. Then the stratosphere extends 30 miles from the Earth. That's the outer region of it, anywhere from 11 to 30. Mesosphere, 55 miles out, and the thermosphere, 80 miles out. Now, there's not a whole lot understood about the levels of the Earth's atmosphere, but one thing that's very interesting, you notice the alternation here between decrease, increase, decrease, increase. That's a measurement of the temperature as you extend yourself out in whatever sphere you're in. Troposphere, for example, the higher the altitude, the lower the temperature goes. When you get into the stratosphere, it does just the reverse. The higher the altitude, the greater the temperature. Just the reverse in mesosphere. The higher the altitude, the lower the temperature, and so forth into the thermosphere. The higher the altitude, the greater the increase in temperature. Now, the temperature in the thermosphere ranges anywhere from 100 to 3,000 degrees Fahrenheit. That's how hot it is. Now, your mesosphere, well, even your stratosphere is extremely cold. Even though there's an increase in temperature, it's an increase from what? I mean, if you're increasing from 500 below zero and you get up to 100 below, you're still cold. So just because it's an increase doesn't mean it's hot. The stratosphere is very cold. But the thermosphere is very hot. Now, you got to be following along, and you'll see what I'm leading up to. We're talking about the water vapor canopy. What's one thing you need to keep water in a vapor form? High temperature. You can't have water in a vapor form with a low temperature. You have to have a high temperature. And here's the answer. Here's our need of a high temperature region, the thermosphere. So this is where the pre-flood, the antediluvian water vapor canopy would have been placed back in chapter 1. It would have been converted from its liquid state into its vapor state, and then it would have been propelled up into this region. And since water vapor is much lighter than air, and water vapor is much lighter than most of the other gases that you find in this region, since water vapor is lighter than air, then once you get it up here into the thermosphere, it's going to be there forever. Nothing could cause it to come down. It's going to be there. So to summarize what I've said, with the thermosphere and its high temperatures, it provides an ideal place for the antediluvian thermal blanket to be placed. And since water vapor is lighter than air, then once you get it into the thermosphere, it's here to stay. But we've got a problem. It didn't stay. Something caused it to come down. Once you get it there, it's there to stay, because you've got the two things that you need. You've got the temperature, and you've got it remaining in a state of water vapor, which keeps it lighter than air so that it won't fall. You see, rain as droplets becomes heavier than air, and that's why it falls. But water vapor weighs much less than pure dry air does. And that way it can float in air, and the air won't affect it at all. And of course, it's much lighter than most of your gases, like CO2, and some of your other gases that you're going to find in this region, so it's going to be able to stay up there in that region. On above that, ionosphere is really no concern of ours now, because we don't need to get up that high in finding a place for the pre-flood, the antediluvian thermal blanket water vapor canopy to be placed. Now I said that once it gets to this region, then we've got it made because it's there to stay. At the same time, we know that it condenses out in Genesis 7:11. It didn't stay there. Now, it stayed for several hundred or several thousand years there, which is rather interesting. It stays there a long time. It doesn't come down. But all of a sudden, at the time of Noah's flood, in Genesis 7:11, the water vapor condenses out as liquid precipitation and then falls. And it hasn't done that prior. Remember, there's been no rain, no clouds. The earth was watered, Genesis 2:5, by a mist. The Hebrew says by an ed, by a mist that covered the earth, which would have been one of the results of having the earth covered with the pre-flood water vapor canopy. Well, we've got to come up with an answer of what caused it to fall. There was a natural process again. God using the natural processes, but there's a natural process again which caused it to condense out as precipitation and to fall. What causes rain to fall today? You see, as long as you've got moisture in the Earth's atmosphere, it's going to stay just like that as water vapor until a certain thing takes place. There are other things that have to take place afterwards, but basically there's one thing that has to take place in order for rain to fall. Now, you're getting a whole lesson tonight in science as well as in Earth history. You have to in order to understand this. The title of the message, by the way, is Volcanism and Sedimentary Activity. So that'll tell you what you're in for tonight. Volcanism and Sedimentary Activity. Back to our subject of what caused it to rain. You see, you might think that the rain pretty soon just gets so heavy up there that the cloud, can't hold it. I mean, what's a cloud after all? And it slips right through the cloud. Well, the cloud is made up of moisture, and some of it's actually liquid in the clouds. Not all of it's water vapor, because it has to coalesce before it can actually condense out as a precipitation in the form of rain. Well, what causes all rain to fall today? We have to answer first of all, and then we'll get to the subject of what caused it to fall. There's one particular thing that causes rain to fall today, and it's known as condensation nuclei. Before water vapor can fall in the form of rain, it has to have particles known as condensation nuclei Self-explanatory. Nuclei means the center, and it's a center around which water vapor is going to form so that it can condense. That's where you get the name condensation nuclei. And rain won't fall. Water vapor will never convert into falling rain and fall if you don't have condensation nuclei. Now, you might not have known that, but it doesn't just sit up there and all of a sudden, I mean, you have to think about these things. What causes it to rain? All that moisture is up there, but sometimes you've got a cloud that passes right over you, and it doesn't let down any water. It's got plenty of it in there. You can tell it's got plenty, but nothing ever happens. None ever comes down. It takes enough of condensation nuclei to be in that region, in that realm, before the water vapor is going to condense out as precipitation and fall. And the chief substance that substitutes as a good form of condensation nuclei today is salt particles that come from the waves and from the spray of the oceans. Remember, the oceans cover 71% of the Earth's surface. So you have plenty of salt particles around which water vapor can form and thereby condense as falling rain. Now, the waves that beat against the shores and the spray that comes up whenever a wave beats against a barrier, that's all very important as far as the earth is concerned, because it's all that mist and all that spray which propels tiny invisible salt particles into the earth's atmosphere, which get up high enough into the region so that the water vapor can form around it. Thereby you've got a condensation nuclei, and it will fall out as rain. But didn't we have oceans prior to Genesis 7? They had oceans in. Chapter 1 says that he divided the waters below between seas and land, dry land, which he called earth. So we've got oceans, or we've got seas during this time period, and they're going to have spray, and they're going to have mist, because as long as you've got a moon, then you've got a rising and the falling of the tides. And as long as you've got a rising and a falling of the tides, you've got waves in the sea and spray in the oceans, and thereby you've got salt particles in the air. So they had the same oceans, the same seas that we have today. They had water that was available on the earth, but yet the water vapor canopy never condensed out. Well, let me give you several answers as to why it didn't. First of all, the oceanic bodies of water were much smaller then than they are today. 71% of the Earth's surface is covered by water today. A much smaller percentage then would have been covered by water. So the oceanic bodies of water were much smaller during that time period. Anyone think of another reason why? Salt, all right. The salt, remember, was not as great in the seas of that day as compared to today. Why? What's salt in the oceans caused by? Runoff of the land. That's always what causes salt in the oceans, is runoff from the land. So since you didn't have any rain, you couldn't have any runoff from the land. You've got only a very, very small percentage of something actually slipping off into the bank of a creek, and that creek went into a stream, and that stream went into a river, and that river went into a gulf, and that gulf went into a sea, and that sea went into the ocean. Very small percentage, because you've got no rain. The more rain you've got coming down on the land, the more runoff you've got, thereby heightening the percentage of the salt content in that body of water into which the gulf, the sea, the river, or whatever empties. So there's less salt in the water. And one final reason is the lack of atmospheric turbulence in the pre-flood era. The lack of atmospheric turbulence. You see, just a wave in the ocean beating against the beach it's not going to carry with it enough force to propel those salt particles all the way practically into outer space. It'll throw them up in the air. But then what do you need? You need a lot of wind that'll catch those invisible particles of salt and carry them high enough to get them in the same region that the cloud is in. Now remember how high this water vapor canopy was. All the way up, 80 miles above the Earth's surface, you're going to have the thermosphere. This is where the water vapor canopy is located in Genesis chapter 7, or it's been there since Genesis 1 for several thousand years in between Genesis 1 and Genesis 7. So you're going to have a tremendous amount of turbulence. As a matter of fact, it's pretty much an impossible amount of turbulence as far as wind systems are concerned in order to carry whatever little amount of salt you have and whatever small oceanic bodies you have into that region in order to provide the water vapor with condensation nuclei. I'm laughing because some of you are just sitting there staring. You don't know where to start or where to end on a sentence. Let me summarize then the 3 points that I just gave you. I'll try to summarize if it gets too difficult. We were asking the question, since we had oceans prior to Genesis 7, and since we know that today it's the salt particles from the waves and spray in the oceans that causes rain to fall because it provides condensation nuclei. There I go again in a long sentence. There's no way to explain it, you see, but in a long sentence.
For the continuation of this message, please turn the tape over.
We were asking the question, since we had oceans prior to Genesis 7, and since we know that today it's the salt particles from the waves and spray in the oceans that causes rain to fall because it provides condensation nuclei. There I go again in a long sentence. There's no way to explain it, you see, but in a long sentence. But since they did have the oceans, they had bodies of water as we have bodies of water, why didn't the water vapor condense out as falling rain? And I gave you several reasons why it didn't. First of all, the bodies of water are much smaller back then. Therefore, since you've got less available water, you have less available salt in the water. Even if the water was just as salty then as it is today, since you have less amount of water, you still have the less amount of salt. Then secondly, there was not as much salt in the oceans of that day because since we had no rain, we had no runoff of the land. And then thirdly, we didn't have the atmospheric turbulence, which characterizes universally our climate. When I say our, I don't mean just North America, all over the world, the atmospheric turbulence, which is needed in order to carry the particles of salt high enough into the atmosphere to place them in the same region as the water vapor is. Now, once it gets up there, they have to coalesce. Coalescence is another subject I don't want to get into because it's difficult, but you can actually, just to sum that up, you can actually have water vapor that forms around a particle of condensation nuclei and thereby comes into the state of a liquid type and yet never falls because it still has to go through coalescence before you get enough of these drops that form into one drop that becomes heavy enough to fall. So that wasn't what caused the collapse. What was it that provided? I've already said that the volcanoes caused the collapse. What was it that provided the necessary condensation nuclei to get into that region, 80 miles up or however far? We don't know how high the thermosphere was at that time. It could have been lower, but regardless of how high, what was it that caused condensation nuclei to get that high? It was volcanoes. It was the magma, the rocks, the dust, the steam, the water, etc., the all other types of debris that would have been thrown out of the mouth of the volcano that it would have propelled it that high, and you're going to have the whole Earth's atmosphere filled with particles of dust that'll be a perfect condensation nuclei. around which the water vapor can form and condense out as falling rain. Now, it's very interesting that when you study the Earth's surface, you come across basically three types of rocks, or three types of rock formations that you're probably familiar with from science in grade school. You've got your metamorphic rocks. What is a metamorphic rock? It's a rock that's gone through some type of change in its composition on the basis of three very interesting things: water, heat, and pressure. And it completely changed the composition and the makeup of the rock. You know, if you put something under enough pressure at a high enough temperature, you can change all the properties of it. Well, take water, for example. You put water under a certain temperature, 212, and pretty soon you've changed the whole makeup of what you had there at the beginning. It's still water, but it's no longer liquid. It turned into steam because you got the right temperature to change it. Now, this is true with all types of things, that you can change them. But you've got metamorphic rocks, you've got sedimentary rocks, which are formed by the movement of sediment in waters, dislocating them from one place, depositing them in another, and then compressing them together, such as shale and sandstone. Those are two examples. It's a rock that's easy to break because it's made up of sediment, so it's called a sedimentary rock. Now, the reason I'm giving you all three of these is because all three of them, you see, geologists can't figure out how all three of these rocks got formed. But if you'll notice carefully in the description of the makeup of the rock, the flood is the perfect thing that could have formed all three types of rocks. It's going to be carrying sediment everywhere. I mean, if you've got a flood over the whole Earth's surface, you're going to carry sediment from Russia to North America and then deposit it there. You're going to have so much water and so much weight per square inch, you're going to compress that. If you've got the right material, you're going to end up with sedimentary rocks. Metamorphic rocks, you've got pressure, you've got heat caused by the magma from the volcanoes, and you've got water that came from the antediluvian thermal blanket. You've got the necessary ingredients there to compose metamorphic rocks. And then thirdly, you have igneous rocks. It's a word that comes from the Latin word for fire. It means fire rocks. And much of the Earth's surface is covered by igneous rocks. Now, igneous rocks, that's simply another name for lava. Lava is a type of igneous rock that's been formed by the fire in a volcano. Now, you might not be able to comprehend with your mind how fire can actually change a rock. You think, well, a rock is so hard, nothing could change a rock. Well, do you know what magma is? Magma is liquid rocks. That's what magma is, liquid rocks. When you see lava flowing down the side, that's magma. That's liquid rocks that's flowing down the side. So, well, that's a contradiction. For it to be a rock and to be liquid, well, it melted the rock. And once it deposits, it's in a region and it begins to cool off, and you end up with your huge lava beds and lava flows all over the place that are comprised of igneous rocks, and much of the Earth's continental surface, as well as its surface under the seas and under the ocean, has been found to be composed of igneous rocks. Now, I don't mean like a small percentage. One good example is the Columbia Plateau in the northwestern United States, which takes up all of the states of Washington, Oregon, Idaho, and Northern California. And you've got a region of 200,000 square miles known as the Columbia Plateau that is made up of nothing but igneous rocks. Now, what that tells us is somewhere in that region at some time in the Earth's ancient early history, you had tremendous volcanic activity somewhere in that region. And we're still having it today. Mount St. Helens is a prime example. Still having it today. Mount St. Helens may have been one of the ones that erupted, may have been active in Genesis 7:11, lay dormant for a century, and then become active again, lay dormant for 5 centuries, become active again, and then become active, just a couple of years ago. And if you followed any of the accounts of Mount St. Helens, it was no small thing when Mount St. Helens blew off its top. It buried cities in that region. Now, the people have been warned, because we've got scientists that stay perched on the top of these volcanoes with their thumb next to it to see if it rumbles any. And it starts to rumble. It's the goddess of volcanoes is about to belch, and it's time to either throw a human sacrifice into the crater, which is what natives in some countries still do. When it starts trembling, get up on the crater and throw a couple of people in there to appease the god down in there. Or if you don't believe in nonsense like that, then you just start warning everyone that God's not causing this. It's a natural process, and it's fixing to cover up this entire region, this entire area. Another thing that we find throughout the Earth's surface are known as ossiferous fissures, O-S-S-I-F-E-R-O-U-S. Ossiferous fissures, which are indentations in the Earth's crust that are filled with bones and remains of prehistoric creatures. You find a lot of your bones in ossiferous fissures. Now, what geologists have noticed today, or volcanologists, those that study volcanoes, have noticed today, is that lava doesn't have to come from a volcano as you think, it being a cone, and it gets smaller at the top and it comes out the top. But lava has been known to come right out of simply cracks in the Earth's surface. And evidently there were a tremendous amount of these in the pre-flood era, or they came about as the flood came about. They were one of the things that helped cause the change in metamorphic rocks, because there you've got the necessary heat and steam and pressure and water and so forth available to do that change. But it's interesting that in these ossiferous fissures we find a whole lot of bones. There are indentations in the Earth's surface, and after you've got the flood, then of course water is going to always seek its lowest level, and a lot of water ran back into these places. They began to close up with a lot of sediment, and it sucked all the bones right in there too. Bones that would have been lying up on the top of these ossiferous fissures would have been sucked down inside as all the water began to go back down inside the earth, or as that simply closed up there. You get enough sediment in there and enough rocks and debris and so forth, it's going to stop those holes up. And there's just hundreds of those all over the place. Now, the Columbia Plateau is just one example of a tremendous region of the Earth's continental surface that's covered by igneous rocks. You can find it in Russia. You can find it on every continent. As a matter of fact, you can even find it in places like Antarctica. We haven't discussed much about Antarctica, but there are volcanoes, extinct ones there, coal fields that are larger than any we've ever discovered that are found in Antarctica, as well as fossil remains and some bones of some animals. I want to give you some examples of some volcanoes to show you the tremendous power that they have. Unless you've studied this, the subject of volcanism, you probably don't realize just how powerful they are. And I picked out a couple of examples that I found that will, I think, vividly illustrate how strong a volcano is, that it does have the power of shooting dust or whatever it wants to shoot miles and miles and miles into the Earth's atmosphere. Now, if you remember the thing about St. Helens, it blew dust into the atmosphere that fell in places hundreds of miles from there. It fell in Canada, it fell in Montana, because this is the way the winds would have been going. And it caused a lot of problems for a lot of people in that region. And once you have a volcano go off in an area like that, see, it just literally destroys all the forest and wildlife and everything around it, and pollutes all the rivers and all the seas. And I remember seeing a program not too long ago about Mount St. Helens, that they are just now beginning to really experience some of the tremendous after effects because of all the mud that came down the side of the volcano. and it's been crashing into trees, and you see when it goes through a forest, it wipes the whole thing out, and you lose all of your necessary vegetation to hold the soil down. And when you lose that vegetation, then you've got tremendous soil erosion, and the next thing you end up with is floods. And they're having a tremendous time in that area right now, although the volcano was several years ago. The actual eruption and, someone getting buried in lava, that did take place. People were buried right in their automobiles with lava. But that's not the worst of it. We're seeing the worst of it now, because whole towns now are having to be evacuated because of the floods that are caused by the mudslides in that region. So they carry with them tremendous destructive powers, many of which you might not realize. One example, 4600 BC. Way before most of the Bible stories, a long time ago, 4600 BC, this wasn't back in Palestine, this was right here in this country in the Cascade Mountains in Oregon. A 12,000-foot mountain by the name of Mount Mazama, M-A-Z-A-M-A, erupted and blew 17 cubic miles of rock from its top. Now you know what a cubic mile is. That is a mile in all directions, sideways, deep, and from top to bottom. 17 cubic miles of mud and debris from its top, thereby reducing its height by 5,000 feet. Then the core of the volcano collapsed, water filled in, and what was the result? Maybe some of you have been there. It's a national park now, and it's beautiful. What was the result? Crater Lake in Oregon. Anyone ever been to Crater Lake? It's beautiful. To its tremendous depth of 1,932 feet. That's deep for a lake. 1,932 feet deep. Crater Lake. That's what a volcano did. Blew its top off, reduced it from 12,000 down to 7,000. 17 cubic miles of mud and rock were blown off its top. Then the core collapsed, it caved in, water filled it, and you end up now with a national park based around Crater Lake in the Cascade Mountains of Oregon with a depth of almost 2,000 feet. Another example is Mount Thera, T-H-E-R-A, which was a volcanic Aegean island. You see, most of your islands are formed by volcanoes. Hawaii, most of your islands are extinct volcanoes, are the remains of a volcano in that region. So Mount Thera was a volcanic Aegean island. Now you remember from the book of Acts where the Aegean Sea is, I trust. 1520 BC, around the time of Moses, exploded, causing 32 square miles of the island to sink into the sea, in some places to a depth of 1,300 feet. It just blew up and blew so much in so many directions that the whole island, or 32 square miles of it, just sank 1,300 feet below the surface of the water. And it completely erased the famous Minoan civilization, an early civilization about which we know very little, but it's very famous of the remains that we have, like the Linear A and Linear B scripts from Mycenae, in the Mycenaean civilization. The Minoan civilization is an ancient and famous civilization, but they were wiped out as a result of one volcano. In the 1st century, another example, in the 1st century AD, Mount Vesuvius erupted and completely buried the two cities of Pompeii and Herculaneum. That was, I think, around 79 AD. towards the end of the 1st century. This would have been not long after Paul's death, still during the time of the Apostle John. In Italy, Mount Vesuvius erupted and completely buried cities, and it had been rumbling for several days. And of course, there are a lot of sayings now about Pompeii and Herculaneum because they were an idle people that had so many pleasures around them. They thought, oh, nothing will ever happen to us. We're safe and secure with our carnal pleasures that we have. One day they were. The next day they were completely erased from the scene of history. Now, Pompeii has been excavated since then, and they have found people in walking positions, the remains of them just charred right in that position by hot mud that had flowed right into the city. And you've got people that had actually been sitting down, people that have been walking. You've got people actually lying down in beds, and the beds in some states are still preserved there because of the hot mud came around it, cooled, solidified, and held its subject entrapped and entombed right in that position. And they've excavated and found food that they were eating and all that they were doing at that time. But when that volcano went off, it buried the 2 cities. Now, you see, you can't outrun a volcano when you're that close to it. You think that you can take off running real fast. But here's 2 cities. No one escaped. No one. From Herculaneum and from Pompeii. Mount Vesuvius completely annihilated both of these cities. Now, a more modern example took place almost a year ago from today. Or 100 years ago, from today. August of 1883. The Indonesian island Krakatoa, K-R-A-K-A-T-O-A, Krakatoa. Of course, that was the East Indies then, but it's Indonesia now. Blew up in August of 1883, and the eruption was heard 2,000 miles away. Someone heard it go off 2,000 miles away. Dust from the volcano blocked the sun for 100 miles around the island of Krakatoa. Couldn't see the sun for 100 miles around this region. That's how much dust went into the Earth's atmosphere. That's why with the eruption of your major volcanoes, you are reducing greatly the Earth's temperature. Because you get so much dust in the atmosphere, then it serves as a retardation of solar energy from the sun. The sun's warmth and energy can't get to us. You have enough volcanoes go off, you get enough dust in the air, and you're breaking up and breaking down the Earth's atmosphere so that the sun can't get through to us today. Just the reverse of that is why people are concerned about aerosol, because it destroys part of the Earth's atmosphere and it lets too much sun through to us, too much sun's radiation. That's why they're always concerned about these deodorant aerosol spray cans. Now, if it's some other besides spray, you're safe. But if it's a spray can, think of everyone that's spraying deodorant around the world, and that's aerosol. And that stuff, most of it doesn't go on you. I mean, they need to make something. That's, I guess, why they made the stick kind. Then it goes on you. But you waste half of the can in spraying it. It goes all over the room. And once it gets in the room, it goes out the window. Then it goes straight up in the Earth's atmosphere and destroys some of our necessary atoms and molecules and gases in the Earth's atmosphere, which help protect us from the radiation of the sun. All of you are staring. Have you never heard of the arguments over aerosol cans? Okay. There have been a lot of arguments over it. Okay, back to Krakatoa. The dust blocked the sun for 1,000 miles around, and it went into the atmosphere so far that it affected all of the Earth's sunsets until the end of that year of 1883. The Earth all over saw spectacular sunsets as a result of the dust that had blown up from this one volcano. That's what one volcano can do. That's why I'm giving you the examples. Just one volcano changed the sunsets that people saw all around the globe. You put so much dust in the atmosphere, and then that's what causes the light refraction, and you end up with orange and red and all the beautiful colors. Now let me give you one other example that's quite a bit more recent to show you how fast they can grow. I remember reading about this years ago before I was ever in Christ, and it was frightening to me whenever I read about it. Maybe you remember the story. It was the volcano known as Paracutin, P-A-R-I-C-U-T-I-N. On February the 20th, 1943, 180 miles west of Mexico City, Paracutin volcano began to grow out in a cornfield. This is how fast they grow. The first day it began to grow. The very first day it was the size of a molehill, and it began producing smoke and steam out of it. This was on February the 20th, 1943. And this is well documented in National Geographic magazine and stuff like this. By the second day, it was 100 feet tall. In 2 weeks, it was 450 feet tall. In 8 months, it was 930 feet tall. In 2 years, it was 1,020 feet tall. And when it finally stopped growing in 1952, it had reached a peak of 1,350 feet. And in that 9-year process, it had buried 2 Mexican cities. You see, if you're very close to it, if it's a mile from you and it begins to grow, then of course the top of it's going to be small and its base gets larger and larger and larger. And pretty soon, if you're a mile or 2 miles away, your city ends up slanted, sitting right on the side of that volcano. Before you know it, you get carried up high enough that it turns your whole city upside down. And if that doesn't destroy it, then the lava that comes out of the volcano will destroy it. Now, with these few examples, I think it adequately shows us what could and what probably did take place back here in Genesis 7:11 when all of the fountains of the great deep broke up. Many of these fountains would have been volcanoes, and they would have had the capacity of throwing so much dust into the Earth's atmosphere that you would have so much available condensation nuclei that it could have begun to rain very fast and very hard. And that's where we get so much rain coming down 40 days and 40 nights. Because normally you don't have enough of a concentration of condensation nuclei in a region in order to produce the rain that was produced in that day. But with these volcanoes going off, then you've got all of these side benefits, or really not benefits, side catastrophes. As a result, you've got the heat and the steam necessary to metamorphosize certain rocks, and you've got the lava and the magma that's going to produce the igneous rocks. You have the dust and debris that's going to produce the condensation nuclei. You're going to have all types of side, quote, benefits, unquote, in bringing about the destructive purposes of God that he had at this time. It was a fearful time in which to live, because you would have heard volcanoes going off. They heard this one from Krakatoa 2,000 miles away. And that's how fearful it would have been. It wasn't as serene as some people make it to be, that in Genesis 7 it began to sprinkle. And then people, went on about their activity, and then it rained some more, and they went on about their activity before they finally got on the ball and tried to get inside the ark, if it was anywhere around in their region. Because whenever you've got these, you've got to have these volcanoes going off in order for the rain to fall. Remember what it says here in 7:11. This is what shows it's supernatural, although God's using natural processes. It says that the same day, all the fountains of the great deep were broken up. It wasn't a process. There was rumbling, for several months ahead. All of a sudden, you've got the tremendous explosions. The same day, all of the fountains of the great deep were broken up. And they would have propelled into the Earth's atmosphere the dust necessary to bring down all that water. And that's why it's placed first, because after that, then he says, and then the windows of heaven were open. Because you're going to have that up there in order to end up with the water, the moisture, coming down in a liquid form as we know it to be rain. Now this would have also caused tremendous sedimentary activity, with the volcanoes erupting and the earth and its surface shaking. There would have been literal vibrations all over the earth's surface. With it doing this and with the waters beginning to come down, then you're going to have tremendous sedimentary activity, which is what has caused some of our great and unique earth features, such as your bridges that you find in more places than just the desert southwest, where you've got, look, it's a stone bridge is what it is. You've got them several places, but a stone bridge, and there's a hole right through the middle of it, enough for a semi to drive through. What caused that rock just to have a hole in it there? Well, you've got so much turbulence and rushing water would have borne its way right through a rock like that. You see, if you've been around an old house where you've got a dripping faucet out back and underneath a concrete slab, and it's been dripping since 1943 or 1942 or however long, what have you got there? With one drop of water, it'll bore a hole right through that piece of concrete. People don't realize how strong water is. There's one example. And all that is one drop of water. But you let it hit and hit and hit. You might not think water is stronger than concrete, but you better think again, because it is. If you have enough of it and you have it concentrated at a certain region like that. Get that water, drip, 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 it'll bore a hole right through that piece of concrete. I've seen a lot of them like that. You'll have an old air conditioner outside that drips every summer. And you've got, your concrete under that, and what happens? You'll bore a hole right in the concrete because of that. So this is what's brought about all of our sedimentary changes that we have. And, well, I guess we're going to have to save some more of that for looking at next week, because I want to get into some more of what happened to the Earth's surface and to the Earth's atmosphere as a result of the water coming down and the dust going up, as we begin to shift gears and look at the physiographical effects of the flood.
For a complete list of Brother